Okay, folks, so in this section 4.5 pre-work, I'm going to look at the second derivative test, which you've actually already done in some of your homework problems, actually way back in section 4.3, but we didn't formally talk about it, and so now I'd like to do so. So the second derivative test, as opposed to the first derivative test, which we did earlier, says that if f double prime is continuous on some interval containing c, with f prime of c equal to 0, then if f double prime of c is greater than 0, f has a local minimum at x equals c. So I want to pause for a moment and just look at why that appears to be true. Okay? So if we've got an interval for which our function is always concave up, and somewhere on that interval, at some point c, the first derivative is 0, then we have a horizontal tangent line there. Well, the only way you can have a horizontal tangent line on a concave up interval is if that horizontal tangent line occurs at a local minimum. So that's why, if you already know the first derivative is 0 at a point, and then you learn that the second derivative is concave up at that same point, then you must have a local minimum there. Okay? Of course, this relied on the second derivative being continuous. That's what allows us to say this. So we can continue. It says that if f double prime of c is less than 0, then f has a local maximum at x equals c. And again, the picture goes like this: if you've got a generic concave down interval that looks like this, and on that, so this function f is concave down on some interval, and there is a place on that concave down interval where you have a horizontal tangent line. The only way that can happen is if you have a local maximum. So the second derivative test is not quite as powerful as the first derivative test, but it's faster to use, and we're going to see some nice applications of it in this section. But one way in which the second derivative test isn't as powerful is that if f double prime of c equals 0, then the test is inconclusive. So the test fails if the second derivative is also 0 at a point where the first derivative is 0. That is, the second derivative test isn't able to determine whether you've got a maximum or a minimum there if it comes out to be 0. Okay, so let's go ahead and sort of parse out the differences between these two tests. So we've already learned the first derivative test, but then we're going to compare it with the second derivative test. So in either case, if you go to do one of these two tests, you're going to have to first find the first derivative, which gives us 2x minus 6 in this case. And let's find the critical numbers of f. Well, in this case, f is defined everywhere. And so then, sorry, in this case, f is defined everywhere, but so is f prime. And so the only place we can have critical numbers is if f prime of x equals 0. We set f prime of x equal to 0. That happens when 2x minus 6 equals 0, or this happens when x equals 3. So in the first derivative test, what we do is we take a number line, and on our number line we put our critical values, our critical numbers. And then we're going to take test points, and we're going to plug those test points into the first derivative. So let's see, I think it makes sense to take 0, and let's maybe take 4, and then let's look at f prime of the test point. Well, if we plug 0 into our first derivative function, we have 2 times 0 is 0 minus 6. That comes out to be a negative number, and so we have that the function is decreasing before we get to 3. And then if we plug 4 into the first derivative, well, we have 2 times 4, which is 8, minus 6, which is, I don't know, it doesn't matter. It's positive, and so the function is increasing on that interval. So by the first derivative test, since the function was defined at 3, notice this function was defined at 3, okay, and to the left of 3 we were decreasing, to the right of 3 we were increasing. By the first derivative test, then, x equals 3 is a local min. Okay? That's how the first derivative test works. That shouldn't be anything new there. We've been doing the first derivative test for a long time now. So what's the new material? The new material now is to look at the second derivative test. Okay. So let's see if we've met the conditions for the second derivative. Well, let's first calculate the second derivative. F double prime of x is equal to 2. Okay. So the first thing is the second derivative continuous on some interval around our critical number of 3? Well, yes, it is, because it's always 2. So then what we can do is we're going to plug the critical numbers of f into f double prime. This is new. Okay? Rather than looking at the behavior on either side of our critical number, we're going to look at the concavity at our critical number. So let's look at f double prime of 3. Well, f double prime of 3 says everywhere I see an x in that expression, I'm going to plug in the number 3. Well, there is no x in it, so it comes out to be 2. 2 is concave, well, excuse me, 2 is positive, so f is concave up at x equals 3. Well, if you've got a function that's concave up on some interval around a place where the first derivative is 0, the only way that can happen, so the only way I can have the first derivative equal to 0, meaning a horizontal tangent line, on a concave up interval, is if I have a local minimum. So that means that x equals 3 is a local minimum by the second derivative test. So now I'd like you to go ahead and try, now I'd like you to try number 3 and explore number 4 to see what's going on there, to see why the second derivative test isn't always as good as the first derivative test, and work through those before you move on to the next batch of videos. As always, if you have any questions, let me know. Bye-bye.